Hello. 지난 시간에 we talked about enantiomer. We'll continue discussing about the stereochemistry at tetrahedral centers. And we talked about the enantiomer last time. We'll talk about diastereomers. We'll continue to talk about the isomers. This is again the diagram of the classification of isomers. We know what the constitutional isomers is, all right? They are isomers with different arrangement of atoms. It's very clear to tell whether they are constitutional isomers or not. Now, in this chapter, we moved to the stereoisomers, introducing chiral centers. If the compound contains the chiral center, and the compound cannot be overlapped with its mirror image with the chiral centers, then we call enantiomers, right? If compound contains more than one chiral center, usually have a mirror image stereoisomers, and we call this as enantiomers. We know it. However, in addition, they can have a stereoisomeric forms that are not mirror images. In that case, we call diastereomers. In other words, if the stereoisomers are not enantiomers, then they must be diastereomers, all right? So the compound with the chiral centers, which are not enantiomeric relationship, then we call diastereomers. Most of those kind of diastereomers with chiral centers are usually called configurational diastereomers. There are specific kind of diastereomers called cis-trans isomer. We already know what the cis-trans isomers, right? But people, even though cis-trans isomers do not contain any chiral centers, people usually classify the cis-trans isomer as a kind of diastereomers, right? So diastereomers include the traditional concept of configurational diastereomers and also cis-trans isomers, right? Some people classify these cis-trans isomers as a geometric isomers, but in organic chemistry, people usually classify isomers into constitutional and stereoisomers, and the stereoisomers can be classified into two different kinds of stereoisomers. One is enantiomers with a mirror image, and the other one is diastereomers with non-mirror images. And most of the diastereomers with the chiral centers belong to configurational diastereomers, but some of those stereoisomers without chiral centers is the cis-trans isomers. Let's take an example for an enantiomer and diastereomer. This is amino acid. It's a threonine. We can easily tell there are two chiral centers here. Number 2 and number 3 carbons are chiral. Because you have two chiral centers, each of these chiral centers can have R or S. Therefore, we can imagine 4 stereoisomers because you have two chiral centers. If you know the number of chiral centers, we can easily calculate the number of isomers by 2n, power of n, 2 power of n, right? Now, we can clearly tell what kind of isomers we have because we have RNS at 2 and RNS at 3. So the four stereoisomers will be like a 2R, 3R, 2R, 3S, 2S, 3S, and 2S, 3R. That's 4 cases. Because we have R and S in each carbon 2 and 3, we can easily draw the structure like this. For example, if you draw the structure of 2R, 3R, it will be like this. Also, if you look at here, this is going to be this is going to be R, and this is going to be R. This is the mirror image. Okay, let's consider this is a mirror, and this is a mirror image. All right, and so this compound has a structure like this. Because they are in a mirror image relationship, R will be changed into S, and this 3R will also be changed into S, because they are in a mirror image. Therefore, threonine, which has a 2R 3R configurations, will have a mirror image relationship with 2S 3S. I told you that there are 4 isomers. Now we talked about the 2 out of 4. Now what are the other 2? The other 2 will be like a 2R 3S, and this is 2R, this is 3S, and here is the mirror image. So same as this. Therefore, this one will be, this is 2R 3S, this should be 2S 3R. Now we have all 4 isomers, 2R 3R, right? Now we know 2R 3R and 3S 2S 3S will have a mirror image relationship, and 2R 3S and 2S 3R will have a mirror image relationship. However, what's the relationship between 2S 3S and 2R 3S? They are not in a mirror image relationship. If 2 isomers are in a mirror image relationship, we can call an enantiomer. Therefore, 2R 3R and 2S 3S, they are in a mirror image relationship, and we can say the relationship between these 2 isomers is an enantiomer. And 2R 3S will be in a mirror image of 2S 3R. Therefore, we can say these 2 isomers are in an enantiomeric relationship. How about these two? What's the relationship between 2R 3R and the 2R 3S? We call it diastomeric relationship, right? How about these two? These two are also diastomeric relationship. These two are also diastomeric relationship, okay? These two are also in a diastomeric relationship, all right? Let's summarize it. Now you have 2R 3R isomers. Now there is one enantiomer which will have the configuration of 2S 3S. Now rest of them, we can imagine 4 isomers. Rest of them, the other 2 isomers will be a diastereomer of this, okay? Now if you pick up 2S 3S isomers, we can easily tell the enantiomer will be 2R 3R. And all other rest of 2 isomers will be in a diastereomer relationship. Okay? Rest of them are the same thing, right? We can apply the same concept to the other isomers. And we can clearly distinguish an enantiomeric relationship from diastereomeric relationship for a threonine amino acid. Let's take a look at other examples here. In this case, it has slightly different structures, right? It's not a threonine, but we can still put the number here, 1, 2, 3, 4, and we know there are 2 chiral centers here. This is chiral, this is also chiral. So we can think of R and S for carbon number 2 and carbon number 3. So we can imagine, we can say that there are 4 isomers, 2R, 3R, just like a threonine, right? 2R, 3R. And we can imagine the mirror images of 2R 3R will be 2S 3S. Another isomer is like a 2R 3S. In this, the mirror image of this 2R 3S will be 2S 3R. Now, let's try to see whether they can be overlapped or not. Okay, let's try to overlap these 2 isomers. In this case, there is no way to overlap it. Even if you try to overlap it, you can never overlap 2R 3R with 2S 3S. Okay, so these 2 are not the same compound, because they are not the same compound, and they are in a mirror image, and they have a chiral centers, so they are in an enantiomeric relationship, right? However, here, these 2 compounds can be easily overlapped. You see here, Now this is OH, so let's turn it around. Let's flip. Let's carbon 1 to go to carbon 4. Carbon 4 goes to carbon 1. Let's just flip. All right. Then we can easily overlap these two compounds. So in this case, these two are the mirror image, but they can be overlapped. That means these two compounds are the same compound. Because they are the same compound, they are not an isomer. They are not an isomer. They are not even an isomer. They are the same compound. So even if you have 4 chiral centers here, you have 3 isomers, 1 pair of enantiomer, and just 1 compound which is not optically active. This is not optically active, okay, because they are the same compound. They are not enantiomeric. The reason they can be the reason they are the same compound, the reason they can be overlapped with this mirror image is because they have a symmetry plane here, intramolecular symmetry plane. Because they have an intramolecular symmetry plane, if you flip it, then you can easily overlap it, right? So even if you have 2 chiral centers, if you have a intramolecular symmetry plane, there will be 1 pair of compounds which are not chiral. And in this case, this compound which are not chiral due to intramolecular symmetry plane is called meso compound, okay? A chiral compound with chirality centers is called meso compound. They are not optically active, okay? Now, let's try to look at the physical properties of stereoisomers. For example, this is the compound we talked about. This is a tartaric acid. Okay, and this tartaric acid has 2 chiral centers, so we can imagine 4 different cases. But you have intramolecular symmetry plane, so RS will be the same as SR, and they are not optically, they don't show the optical activity even though they have a chiral centers, and we call this as a meso compound. They are the same compound. So this compound, this tartaric acid, has 3 isomers, 1 pair of enantiomer and meso compound. Okay. Let's take a look at the physical properties of these 3 isomers, 1 pair of isomers and meso compounds. If you look at the 1 pair of isomers, plus isomer will have alpha D equals to plus. Minus isomer will be minus 12. Alpha D value will be minus 12, okay? How about the melting point? They have exactly the same melting point because the 2 enantiomers will have the same melting point, but the opposite optical rotation. They have the same density. They have the same solubility. So usually the compound with the enantiomeric relationship shows exact the same physical properties except optical rotation. Okay, they have a opposite sign of the optical rotation. However, if you look at the physical properties of the meso compound, they are different compound from enantiomers, so they will have different melting point. Physical properties different. Optical rotation will be 0 because they are not chiral. Density is different from an enantiomeric pair. Solubility will be different. So the meso compound is completely different isomers, different compound from enantiomers. They will have completely different physical properties, okay? So in this case, the meso compound, the relationship between meso compound and enantiomers will be diastereomic relationship, okay? Because they are not, mirror images, but they have chiral centers. They have chiral centers, but the meso compound is chiral, and enantiomers will be chiral. So the relationship between enantiomer and meso compound will be diastereomeric. Okay. The relationship of enantiomeric, diastereomeric, and the concept of a meso compound might be a little bit complicated. So don't confuse. Try to clearly distinguish definition of meso compound and the relationship of the meso compound with an isomer, and try to understand the relationship of diastereomer relationship between meso compound and enantiomers. Okay. Okay. Now, many cases, if you have a pair of enantiomers, only one enantiomer has a biological activity. That's the general case. Okay, but in many cases, in many synthetic methods, you always produce one-to-one mixture of enantiomeric pairs. So in many cases, you will have a mixture of plus and minus, and usually the relative ratio of plus and minus is 1-to-1. It is very difficult to selectively synthesize plus or minus isomers. So usually you produce the one-to-one mixture of plus and minus by synthetic method. If you have a one-to-one ratio of plus and minus isomers, we call it a racemic mixture. It's a mixture. If it is exactly one-to-one mixture, and then we call racemic mixture. Because you have a one-to-one mixture of plus and minus, if you put this racemic mixture into the polarimeter and then try to see the optical rotation, you will see no optical rotations. Because you have a one-to-one ratio of plus and minus, the optical rotation due to plus and minus will be counterbalanced, and you will see no optical rotations. If you have a one-to-one ratio of plus and minus enantiomers, people try to separate them because we know that only one of them is biologically active, and even the other one is an inhibitor for the other enantiomers. So people always want to separate one enantiomer out of a mixture of enantiomeric pairs, and we call resolution to separate enantiomers from the racemic mixtures. Now, there are a few ways to separate it. The easiest way is to apply the acid-base reaction concept. For example, you have a carboxylic acid, that's an acid, amine is a base, so if you mix them together, there will be acid-base reactions. Acid will provide the proton, base will accept the protons, and it will generate a salt. Okay, that's the acid-base reaction. Now, if you have an acid with one chiral center here, and if you react with a base like a CH3 and H2, for example, let's say this is a mixture of a one-to-one mixture of R and S. Then if you react with CH3 and H2, you will have a mixture of a one-to-one ratio of R salt and S salt. Okay. However, if you react with a chiral base, so let's say this chiral base is just 100% S isomer, and this is the mixture of R and S, that's 1-to-1, right? Then if you react it, you will have mixture of RS. This R comes from 50% of acid, S comes from this base, and this S comes from rest of the 50% of an acid, and S comes from a base. Now, if you react chiral acid with chiral base, I mean, if you react to the racemic mixture of an acid with a chiral base, then you will see RS mixture of RS and SS. That is the they are in a diastomeric relationship. If they are in a diastomeric relationship, they always have different physical properties. If they are in an enantiomeric relationship, like here, 1-to-1 ratio of R and S, there's no difference in the physical properties. So because there is no difference in the physical properties, like a solubility, like a melting point, there's no difference, right? So there's no way to separate them based on physical properties. But if you react with a chiral base and you convert this the racemic mixture of acid into the salt, and they are because they are in a diastereomer relationship, they will have different physical properties like a melting point or solubility, and there will be a way to separate them. Okay, and you have to develop it. We know there is a difference in the physical properties, and you have to develop a way to separate them because using their different physical properties. Okay, we call this as a resolution of enantiomers. Um, uh, this is a typical way to resolve enantiomers. Again, this is review isomerism. This stereoisomers can be classified into enantiomers and diastereomers, and more allowable diastereomers are configurational diastereomers. All right, but we want to classify cis-trans isomers also kind of diastereomers, even if they don't have chiral centers. Because configurational diastereomers and enantiomers, they have chiral centers. We call these two isomers optical isomer because they may have optical activities, optical rotatory activities. However, cis-trans isomers, they don't show the optical rotation, so we classify enantiomer and configurational diastereomer as optical isomer, and cis-trans isomer sometimes we call is a geometrical isomers, right? Don't confuse with the nomenclature, right? This is constitutional isomer. We all know that it's just alcohol, ether. It's very clear they are isomers, so I'm not going to explain it. Stereoisomers, for this is a mirror image relationship, so we can easily tell it's enantiomers. And in this case, this 2R3 R, this is 2R3 S, so they are not in a mirror image, but they have a chiral centers. We know that this is diastereomers, right? This is not cis-trans isomer, right? So this is a configurational diastereomers. We are moving into the chirality of other atoms like nitrogen, phosphorus, and sulfur. For a nitrogen, we know for a carbon you have three atoms or atomic groups bonded to the carbon. But for a nitrogen, you have only three, like this. And because you have one pair of non-bonding electrons. If we count this non-bonding electron as one group, we can apply the sequence rule. But if you look at the atomic number of the non-bonding electrons, there is no atomic number. Therefore, we consider this non-bonding electron as a lowest sequence priority, right? You put this non-bonding electron as a lowest sequence priority and then assign R or S. If you have because you have 1, 2, 3, 4 groups, including non-bonding electrons, we can imagine mirror images, and this will be the mirror images. And these two are the enantiomeric relationship. Okay. However, the nitrogen is so small, and it is known that this non-bonding, the orbitals of this non-bonding electron can be flipped. Actually, you have a very small lobe here, very large lobe here. Okay, but sometimes this small lobe becomes very large, and this large lobe becomes very small. Then in that case, these two non-bonding electrons will move to the opposite side and becomes the other isomers. Actually, for the nitrogen case, these two mirror images are intercompatible rapidly. S isomer becomes R isomers rapidly at room temperature. So interconversion between R and S on the nitrogen-containing compounds are very rapid, and it is meaningless to distinguish R and S isomers of the nitrogen-containing compound. So we usually don't consider any enantiomeric relationship of nitrogen-containing compounds. Okay, we don't consider chirality at nitrogen center. How about others? All right. So here it shows inversion is very rapid. Because they are very rapid, it's almost impossible to distinguish them. Here this is an ice. We know that this is an R because this is the lowest sequence priority, and this is an S. But R and S forms changing rapidly all the time, so we don't consider the RNS forms in nitrogen-containing isomers. How about others? We will consider a similar situation in the phosphorus and sulfur. For phosphorus and sulfur, they are much larger than the nitrogen, and interconversion is much slower. So in this case, this will be 1, this is 2, this is 3, so this is R, right? But if you change this to it, then it'll be an S. I told you this is relatively stable, okay? R or S isomers can be relatively stable. S for the compound is the sulfur. We also consider the non-bonding electrons here, non-bonding orbitals here, and this non-bonding orbital has a lowest sequence priority, and you can assign the numbers and figure out what's the configuration here. We immediately know that this sulfur will have a S configuration. Also, just like a phosphorus, the interconversion of S and R isomers at the sulfur chiral center is not rapid, so we can distinguish R or S isomers based on the configuration of an S. And so phosphorus and sulfur has different situation from a nitrogen. So we can clearly say that, okay, this is an S isomer, S configuration with S adenosyl methionine. There are two isomers, R and S, okay? But I think S isomer is much more stable because of the steric hindrance. Prochirality. This is sp2. So it's not sp3, so we cannot define the chirality of this carbon. We cannot, actually this carbonyl carbon is not chiral. However, if you break this pi bond, if you break this double bond and convert it into here, then this becomes chiral, right? So but depending on where this hydrogen comes from, where it comes from the top side or where it comes from the bottom side, it will produce different isomer. Because even though this carbonyl is not chiral, if double bond is converted into single bond, then it will generate chiralities. Therefore, we call this carbon is prochiral, and we call this carbonyl carbon is prochiral center. All right. Now, if you have a carbonyl here, we have this is plane. This is sp2. We can imagine one plane, and we can define the upper side of the plane, and lower side of the plane, and then these two upper side and lower side can be named differently. The upper side is like you follow the sequence rule. This is number 1, this is number 2, this is number 3. So if you look at from the top, it goes like this. So just like R configurations. So therefore we name the face, upper face is named as Ri face. Okay, the bottom face, the direction will be different. It will be opposite. It will be just like S. So the bottom face is named as C face. Okay, Um, if hydrogen comes from the leaf phase, we know that it will generate S compound. If hydrogen comes from the C phase, it will generate R compounds, okay? So depending on where the hydrogen comes from in the reduction of the sp2 carbon, sometimes it will generate S or sometimes it will generate R. Usually a lot of enzymes are specific. A lot of enzymes provide this hydrogen from re or C phase specifically because enzyme can distinguish whether uh, enzyme can distinguish D phase from C phases. For a double bond, we can also define D and C phase. Okay, the fumarase enzyme add the water molecule to the double bond here. Uh, then also it is stress specific. All the fumarase enzyme is C specific, and you add the OH2 from the bottom side. Okay. For an alcohol dehydrogenase, we have CH2, and this carbon is not chiral, right? However, we can define these two hydrogens as pro-R or pro-S. The way to define it is if you have a methylene hydrogen here, you distinguish one of them by substituting with the deuterium. Okay? And deuterium has a higher atomic number than the hydrogen. You substitute this one with the deuterium, then this one will be the lowest sequence priority, and then assign RNS, and then you find this on R, then we call this hydrogen is pro-R, right? Might be confusing, all right? I'll apply the same principle on to the other hydrogens. Okay, if you have two hydrogens are the same, if they are not, if two hydrogens are the same, but if they are not the same, then you will generate a chiral center. Okay, now you want to name one of these two hydrogens, then you put your substitutes, you replace this hydrogen with deuterium. Okay, and then this hydrogen will have the lowest sequence priority, and then you assign RNS, and then when you replace this with deuterium, and if it is S configuration, then you call this pro-S hydrogen. Okay. Alcohol dehydrogenase is an enzyme. It's stereospecific. If alcohol dehydrogenase can distinguish these two hydrogens, if they can remove pro-R hydrogen only, then they will the pro-S hydrogen will be left, and you will have this aldehyde as a product if it is pro-R specific. If it is pro-S specific, you will remove HS, and then you remove HS, and then HR will be left. Okay, so depending on whether the enzyme is pro-R specific or pro-S specific, the enzyme can selectively remove one of these two pro-R or pro-S hydrogens. That means even though both of them are hydrogens, the enzyme can distinguish them. Okay, here's again, and we know why this is pro-R or why this is pro-S. Okay, you replace hydrogen with deuterium and then assign R or S using this one as the lowest priority, and you find this R, then you come back, and this you name this as a pro-R. All right. We talked about the chirality, stereoisomer, but actually most of the things in nature are in chiral. The easiest example is your hand. Your right hand, your left hand, your hands are chiral, all right? Because your hands are chiral, your right hand or left hand if you have some other chiral compounds, we can imagine the affinity of your right or left hand with the chiral molecules. Okay, for example, here, this is your left hand, and let's say you have a chiral compounds. In this case, you have a green, red, and sky blue is on your hand. It is close to on your hand. But for the other isomers, you will have green here, you'll have sky blue here. But if it is the other isomers, then these two will be switched each other, right? So the blue part will be on your hand side. In this case, red sphere will be on your hand side. You will touching your hand side. So because your hand is chiral, whether the counterpart molecule, whether the counterpart molecule is R or S, those molecules will have a different part contacting your hands. This is the principle why chiral molecule has different interaction with your chiral molecules in your cell. This is why if you have a mixture of two enantiomers, only one enantiomer is biologically active. Okay? Because if you look at these two isomers, they are enantiomer relationship. Okay? But if you look at this your left hand, they have different contacting point. So because they have different contacting point, they will have different interactions, different effect. Okay? Let's take an example. This is a limonene molecule. You have one chiral center. We can imagine plus and minus, all right? Plus is the isomer. Okay? Rotated plane polarized light to the right direction. This is a lever rotatory. It's a minus. In this case, plus isomer tastes like orange taste. However, the minus isomer tastes like lemon. Why does it? Why do they have a different taste? Because if you have a different stereochemistry here, just like different molecules will have different part to touch your hands. Because you have different part to touch your hands, they will have a different taste. Okay. Now, in this case, your hands is just like your the cells to recognize the taste is a chiral molecules, just like your hands. All right. So they can distinguish the chirality here, plus or minus, and they have different. They sense a different taste. Okay. So actually, most of important biological molecule has the chiral centers, and if they have different chiral centers, they have, even though they are the same molecules, even though they are the stereoisomers, if they have different, if they are the different stereoisomers, they will have different biological molecules. Okay. This is electron light beam. This is an intermediate of the biosensitive erythromycin. It's very good antibiotics. For example, here, wow, so many, you can count the number of chiral centers, so many chiral centers. So actually, erythroid light B may have several different kind of chiral isomers, right? And only one of these isomers is biologically effective antibiotics. You can count the number of chiral centers, and because of these chiral centers, if you count the number of these chiral centers, you can easily calculate the number of stereoisomers you can have. All right. Okay, I think this is the end of this chapter. We talked about the very important thing in this chapter, concept of stereoisomers. And one of the most important concept is the enantiomer, and diastereomer, and the meso compound. Okay. Okay, this is the end of this chapter, and see you next time.